Hello viewers, I remain Sadis Yusuf Abdullahi. I welcome you to this second part of our first episode on the topic electromagnetic field. In the first part of this episode, we've been able to establish the fact that there is a vector sum of a particular force which normally exists when you have electric field and magnetic field. This is what we had last part of our first episode. We said the total force is equals to the vector sum of Fm plus the vector sum of Fe. Lastly, we said we have F equals to Q in bracket. We are having E plus V then times B, where we said the Q is the charge, the E is the electric field, the V is the velocity, and then the B is magnetic field. This is what we said. Now, the next thing we are going to discuss, we are going to look at the diagram, the magnetic field diagram, and the current which exists when you are having these two particular forces. Now, here is the diagram. In this particular diagram, we can see that the current moves out. Therefore, the field is now in this particular direction. The current, as the current moves out, the current is in this particular direction. In another word, if the current direction is reversed, the direction of this particular field will also change. When the current is reversed, the direction of this particular field will also what? Change. The force exerted on this particular surface depends on a particular or certain number of factors. I say the force on the wire on this particular current carrying conductor depend on a particular factor. These are the factors. The first factor is number one. We have the current. The current I flowing through the conductor, or the current flowing in the conductor. That is the first factor. The next factor is the length of the conductor. The length of the conductor. The length of the conductor. That's the next one. The conductor in that particular field. Number three is the angle. Number three is the angle between the conductor and the field. The angle between the conductor and the field. And then the last one is the strength of the flux density, or flux density. The strength of the field, which is referred to as flux density. Flux density. In a nutshell, we have current, length, the angle, the flux. The current that is made to pass in the conductor, the length of the conductor in the field, the angle between the conductor and the field, and then the flux density, which is the strength of the field. These are the factors upon which the force on the wire actually depends on. Based on these factors, we are able to establish the fact that F is equals to BIL sine theta. F is the force, B is the magnetic field, while I is the current, and then L is the length, the theta is the angle. Remember, we have 1, 2, 3, 4. These are the factors upon which this particular force on a current carrying conductor depends on. Remember, I said the unit of B is the flux density. The unit of B is in Tesla. We say it's what? Tesla. Or Weber per meter square. Either Tesla or Weber per meter square. I said 1 Tesla is equals to force per unit length. Force per unit length when 1 ampere of current flows through the field at an angle of 90 degrees. When 1 ampere of current flows through the field at an angle of 90 degrees. At an angle of 90. Here is the example. We have a force experienced by a current carrying conductor of length 100 centimeters is 4.0 Newton. Calculate the current in the conductor if it flows in the direction 45 degrees with the field of 1.0 Tesla. Now here is the solution. Here is the solution. We are given the length. The length is given as 100 centimeter. Of course, we are going to have this one converted to meter. So this one gives us 100 times 10 to the power of minus 2. We're converting the centimeter to meter. The force in the question is given as 4.0 Newton. We are asked to calculate the current. So our current will now be question mark. They say if it flows in the direction, that is theta, our theta is what? 45 degrees. Then the field strength, which is B, is given by 1.0 Tesla. From this data, we can easily recall our formula. F equals to BIL sine theta. Remember this formula? This formula is the formula we just ended before this particular example. We're going to proceed. Now we're going to make substitutions now. F is given as 4 equals to, the B there is 1, we say times, the I is not known, then times our L there is, we have 100 times 10 to the power of minus 2,